So if we see this, then we know all the concentrations are 1 molar, and all the pressures are at 1 bar or 1 atmosphere. It depends. And so what we're looking for is, this is the driving force under standard conditions. And so it's a little bit weird. Let's take a reaction that we looked at. Well, actually, this one that we're looking at. This is H2O liquid goes to H2O gas. So under standard conditions, what we need is a vapor pressure of 1 bar or 1 atmosphere. Bar and atmosphere are close. They're just off by a few percent. And so, are we going to have a vapor pressure at 298 Kelvin of 1 bar or 1 atmosphere? And so, when we hit a vapor pressure of 1 bar or 1 atmosphere, what happens to water? It starts to boil. And so what this is asking is, are we going to generate enough vapor pressure at 298 so that it equals 1 bar or 1 atmosphere? And the answer is at room temperature, no. Right? And so this is why delta G is positive here, because we don't, under standard conditions, we don't have a driving force in this case. However, we could change the temperature, and we did that. We changed the temperature, and at higher temperatures will generate a higher vapor pressure, and then we can get this to at least equal 0 or go negative. And so under standard conditions, but maybe under non-standard conditions, how can we do that? And so under non-standard conditions, we need to correct it, and that correction given by this is RT ln Q, where Q doesn't have to be 1 bar or 1 atmosphere or 1 molar concentrations. Q is just whatever concentrations or pressures we have. We'll plug in there, and this is going to be our correction for this. Now, we have to keep track of a lot of things. And so normally what I do is I write little subscripts and this sort of stuff so that I can keep track of things, because it's easy to just write some equation and think you're going to get the right answer. So for example, if I want to know what temperature does water boil at, I might, go. Right now, delta G would be positive, because if I plug in here Q, now Q is the products over the reactants. So in this case, Q would be the products under standard conditions would be 1, and the reactant was just liquid water, which would have an activity of 1. So this would be ln1, ln1 is 0, and delta G is just equal to delta G naught under standard conditions. And so what I want to do is I want to change those to see at what temperature water boils at. And so this is going to be delta G is equal to delta G naught plus, I'm going to solve this actually. Solve it for T, or T ln Q. Let's solve it for T, because I know what Q is. Q is going to be, the partial pressure of the products, which should be 1/3 bar over 1, the activity of water. Just be 1. It's pure liquid. And so this is just equal to 1/3 here. So I'll plug that in here. And then just solve this for T, so it looks pretty simple. Let's subtract delta G from both sides. So we'll get delta G. Actually, what I need to do is I need to set this to something. Right now, it's positive, so I need to set this to 0. That would be the transition from going positive through 0 to negative. And so if I know the transition point at 0, then I can make this negative. And so what I'll do here is I'll just set this equal to 0, and then I'll get RT ln of Q is equal to delta G naught. And then it says solve this for T. T is equal to delta G naught over R ln of Q. And then just plug this in. So what was the delta G naught that I had calculated earlier? It was like plus 8.5?
Yeah, 8.5.
Plus 8.5 kilojoules. And so here, one thing is, delta G is going to be in kilojoules, but R is not. R is going to be in joules. And so I'm going to convert this to maybe 8, what was it, 8.5 what? Just 8. Okay, so we'll just go 8,500 joules. R is, what was R again? 8.3145 joules per mole Kelvin. All right, now the delta G naught, this is per mole. And so this is per mole here, so the moles cancel. And when I see the reaction is written there, the joules cancel, and I'm just left with 1 over Kelvin, which is just Kelvin. And then I can calculate the Kelvin here. But I'm not actually going to calculate the Kelvin because I made an error here. You see my error? Well, no, if I'm under standard conditions, ln of Q would be 0. But Q is going to be ln of 1/3, and we'll just plug in 1/3 there, just calculate it. But I made another error. It's hard to see. This is a very common error. Do you see it? So this is why I like to keep little subscripts going along here. Do I know what the temperature is? No, actually, that's what I'm doing. I'm trying to calculate what the temperature is, right? And so I'm trying to figure out what this is the delta G at temperature T. I want that to be set to 0. So whatever temperature that takes to get it to 0, this is what I want. I want delta G to go from plus 8.5 to 0 to negative. If I can get it to negative, then this is going to start to boil. And so this is going to be the temperature which will start to boil. But the situation here is, okay, this is delta G under non-standard conditions at temperature T, and this is delta G naught under standard conditions, but at what temperature? This is at 298. And so there's a mismatch here because this temperature is not going to be at 298. This temperature is at 298. See that? And so I cannot use this because this is my delta G at 298. Delta G is a function of temperature. And delta G, remember, we used delta G to change it from, what we did was we changed this from non-spontaneous, plus 8.5, to spontaneous. That is, at least go through 0. And that temperature was close to 373 Kelvin, or it should have been 373 Kelvin. That was the problem we did before this. And so temperature impacts the driving force considerably. And so we can't assume that the delta G at 298 is going to be the same value as the delta G at some other temperature T. We can't do that. And so it looks like we're stuck here. However, we're not completely stuck because there are more ways to determine delta G. And so let's take a look at this. So this is going to be delta G naught. What we want is we don't want delta G naught at 298. At 298. We want delta G naught at temperature T. That's what we want. But how can we calculate delta G naught at temperature T when we don't know the temperature?
The H minus delta F.
Yes, yeah, that's how we're going to do it. And so this is the way we're going to do this. we're going to take the, let's take this equation, RT, ln of Q. Okay. Take RT, ln of Q is equal to delta G naught at temperature T, which is some unknown temperature, which is going to equal delta H naught at temperature T minus T delta S naught at temperature T. Now, delta G changes significantly with temperature. However, delta H and delta S do not change significantly with temperature. And so what we're going to do is we're going to make this assumption. And the assumption is that delta H at 298 Kelvin is going to be about equal to delta H at temperature T, and then we'll have minus T, and then delta S at 298 Kelvin is going to be about equal to, actually we made this assumption before in the previous problem. And so we're assuming that delta H and delta S do not change significantly with temperature. And so, let's say we're taking a liquid and going to a gas. If we take a liquid and go to a gas, there's a big entropy change, liquid to gas. But let's say we take a liquid and go to a gas at 25 degrees C versus taking a liquid like water and going to a gas at 50 degrees C. Is there such a big difference? Well, at 50 degrees C, there's going to be more energy. But there's going to be more energy for both the liquid phase and the gas phase. And so it turns out there isn't such a huge difference. And the same thing goes with enthalpy. We vaporize it, we got to break all the hydrogen bonds, and it turns out we got to do the same for both. But when it comes to delta G, we can't make this assumption. This assumption does not work for delta G because delta G is a function of temperature. It's going to change significantly with temperature. And so we can't do that. Okay, so what we'll do is this. We're going to, let's say, put all the temperature terms on one side. And so maybe what I'll do is I'll just add a T delta S naught to both sides. And so I'm going to get RT ln of Q. Now, one thing that happens is this. When delta G is equal to 0, we call that equilibrium. And so at delta G equal to 0, then Q is equal to K because we're at equilibrium. That is, the reaction quotient is equal to the equilibrium constant. And so we could interchange this here since we already set that to 0. And so it'll be ln of Q or K. This is going to equal, RT ln of Q plus T delta S naught is equal to delta H naught. And so this will be at 298, this will be at 298. And then we'll factor out the T, so we're going to get T times R ln of Q plus delta S naught is equal to delta H. It'll be 298, 298. And then solve this for T. So yes, the temperature is equal to delta H naught divided by R ln Q plus delta S. For R ln K. And so the K value that we want, so this equation is quite a bit different than the equation we just had there that I just erased. So I was going to compare the two. But let's go ahead and calculate this now. And so we're going to take our delta H naught at 298 Kelvin. The delta H naught at 298 Kelvin was what, 44.0 kilojoules? Is that it?
Yes.
R is 8.3145 joules per Kelvin. This is per mole of water. Lm of Q we want to be K. You know, what we need to do is, right now, the equilibrium is being shifted back. And so what we want to do is we want to get it to equilibrium, and then we want to force it to the forward direction, basically. So we want to transition. Leave it like that. And then delta F was 118, is that right? 118.8 joule. And so what I'm going to do is I'm going to convert kilojoules to joules. Do 1,000 joules per kilojoule. And so the kilojoules cancel. And then the joules cancel here. And that'll leave me with 1 over Kelvin in the denominator, and bring that to the invert and multiply that. And so let's see what this comes out to. So I'm probably going to do the denominator first. To 1 divided by 3 equals, take the natural log of that, times 8.3145. Plus 118.8. And then invert that. And multiply 44,000. $401 Kelvin. Is that what you guys got?
Yeah.
401 Kelvin. Is that possible? No. This is not possible. This would be like a pressure cooker. We're doing low pressure here. So there's something wrong with my equation here. I think this is what I did wrong. Delta G is equal to delta G naught plus RT ln Q. And so if I'm doing delta G naught here, delta G naught is equal to minus RT ln Q. And so I forgot this here. So I need to fix this, sorry. And so this is minus RT ln Q, which is going to make this minus R ln Q, which I probably should have reversed these, but it's okay. So let me try this one here. The reason is because, again, the vapor pressure should, to get to 1/3 of an atmosphere, should take less temperature. And okay, so second attempt here. 1 divided by 3, natural log, times 8.3145 negative plus 118. 8. Convert. 343. Okay, that's better. 343.9 Kelvin. This is better. Why? Because I know the vapor pressure curve of water. There are different ways we can figure this out. The vapor pressure curve of water looks like this. And the vapor pressure has a temperature, the vapor pressure of 1 atmosphere has a temperature of 373 Kelvin. That's the normal boiling point. But if we're on top of Everest or something like that, then the boiling point is going to be much lower. So we can get that off the vapor pressure curve. In fact, we can determine the temperature at any vapor pressure here using this equation. So this equation will be able to generate this vapor pressure curve mathematically. And so this is going to be how much in terms of Celsius? So about 70.9 degrees Celsius, about 71 degrees C. So what that means is this. If you're trying to cook, let's say you're trying to cook pasta in boiling water, what's the temperature of the boiling water going to be? Well, the temperature is going to be 71 degrees C. How long would it take to cook? Longer. A lot longer. A lot longer. And therefore, high altitudes, what you have to do is you have to cook things longer, otherwise, they don't cook. So 71 degrees C going to take a lot longer to boil. And so the alternative is to use a pressure cooker. If you use a pressure cooker, then we can get higher temperatures. In a pressure cooker, what we do is we just have a greater pressure than 1/3 of an atmosphere. Let's say we had 1 1/3 atmospheres. If we had 1 1/3 atmospheres, then we can calculate the temperature at which what else that is. We'll just set delta G equal to 0. That's when it's going to transition, and then we're going to get an even higher temperature here. And so at low pressures, we're going to have a lower boiling point. At high pressures, we're going to have a higher boiling point. And this means things cook faster. Turns out for every 10 degrees C, roughly, this is for food, but for every 10 degrees C, you double the cooking speed. And so let's say we went from 100 to 110 degrees C, we just doubled it. And so this one, if we start off at 70, we go to 80, okay, 80 degrees C, it will cook twice as fast as it would at 71, and then 80 to 90, double it again, and 90 to 100. And so this is very slow. This is 3 of those.
This is a random question, but how did you relate 1/3 bar to the environment of cooking pasta?
Oh, how I did that was water boiling. Well, boiling water, what do you use boiling water for? Well, that's all I was thinking, cooking pasta or making tea or something like that. And so that's why I related it to that. And so if you were on top of, let's say, Mount Everest, where the pressure is like 1/3 of an atmosphere, how long would it take to cook the pasta? It's going to take a long time. And in fact, we could figure out the calculation. In the next chapter, we're going to be looking at how long things take. That is kinetics. And so right now, we're just looking at the boiling point. So going back to this, so let's take a look at some of the equations and some of the scenarios that we use for calculations. So, under standard conditions, we're mainly interested in delta G. What is the driving force here? And so under standard conditions, delta G, there are different ways we can calculate delta G. We can get delta G under standard by calculating delta H naught minus T delta S naught. Okay, but we have two equations that we use. If we're at 298 Kelvin, that's great, because we can calculate delta H naught at 298 Kelvin and delta S naught at 298 Kelvin. That's going to give us our delta G naught at 298 Kelvin. If we're not at 298 Kelvin, then that complicates things. But if we are at 298 Kelvin, this is not the easiest way. The easiest way to get delta G naught at 298 Kelvin under standard conditions is to use delta G of formation. This is like using delta H as a formation, exactly the same type of deal, where we take the sum of the delta G's of formation of the products minus the sum of the delta G's of formation of the reactants. So this is a bit easier to calculate, but the problem is that this is only for 298 Kelvin. If we're not at 298 Kelvin, but still under standard conditions, then this is what we're going to do. And so if we take delta G naught at a temperature T, so we're under standard conditions but not at 298, then what we're going to do is we're going to just assume that this is going to equal about delta H at 298 under standard conditions minus T delta S naught at 298 Kelvin under standard conditions. And so we're going to assume that delta H and delta S don't change much, and therefore we can calculate the temperature of which, at which we'll get a particular delta G value. So an example of this would be like calculating the boiling point of something. Of water, which we did. And so under standard conditions at 298 Kelvin, the boiling point of water, well, this wasn't favorable. Water doesn't boil at room temperature. And so calculating the boiling point of water at, we saw that the water doesn't boil at 298, but we could boil at higher temperature. So what we do is we take delta G naught at temperature T and set that equal to 0, because under standard conditions at 298, it came out to 8.5. And so what we want to do is we want to get rid of that 8.5. And the way we're going to do that is we're going to manipulate the temperature so that the T delta S term cancels out the delta H term, and we're left with 0. And we can figure out what that temperature is. The temperature is just going to equal, we'll add the T delta S to both sides, and we'll get delta H naught at 298. At 298. This is obviously, it's going to be off a little bit because we shouldn't be using delta H and delta S at 298, but we are, because we don't have the other value. If we had the other values, then we'd use it here. But if we had the other values, then we'd already know what the temperature is. And so this is just kind of an estimate of the temperature. Yeah. And so we got a temperature like 370 versus 373, 371. Something like that, 1 or 2 degrees or 3 degrees off. But, it's okay. Okay, now, what if we're under non-standard conditions? So standard conditions means we have 1 bar, 1 atmosphere, and 1 molar concentration. But if we're under non-standard conditions, then we use this equation. Delta G under non-standard conditions, this is going to be at temperature T, is equal to delta G under standard conditions at temperature T, plus RT ln of Q. Now, it's easy to get this sign mixed up. An easy way to remember the sign here is Q. What happens if Q is big? Well, if Q is big, you have a lot more product than reactant. A lot more product is going to decrease the driving force or increase the driving force. More product you have means the driving force should decrease. If the driving force decreases, then delta G becomes more positive. And so if Q is big, then ln of Q is going to be bigger, which is going to lead to more positive. Now, if I make this a negative, if Q is big, this is going to make it more negative, which is going to decrease delta G, which increases driving force. So that's one way to remember the sign. It's easy to get signs all mixed up. All right, so there are two types of calculations we do for this. One type of calculation was calculating for T, which we just did, solving for T. But when we solve for T, remember what we had to do for this, delta G naught, this is what we didn't have. We didn't have delta G naught at temperature T. And so what we had to do was we had to substitute delta H naught at 298 minus T delta S naught at 298 for this term here, and then solve for T. That's what we did. The other type of problem is we solve for Q. Yeah. What is Q or K? Which we'll talk about, because if we're at equilibrium, we call it K. So if we solve for Q or K, then this is the way we'll do that. Yeah. So we have delta G, the temperature T. We're going to set that equal to 0. So that means we're at equilibrium. And this is going to equal delta G naught at temperature T plus RT ln. But now, if we're at equilibrium, we're going to change Q to K. This is going to be at equilibrium. Yeah.
What if we aren't?
If we aren't, then we just leave it as Q.
Well, then what do we set it?
We don't set it equal. We just leave it as is. That's the way we do it. Whenever you set this to 0, then you change Q to K, which I didn't do earlier, but you should. I mean, it's the same thing, Q and K. It's just, is that equilibrium or is it not equilibrium? And so what we get from this is, okay, we're going to get this K. Actually, let's go ahead and solve this. We're going to get delta G naught is equal to minus RT ln of K. And then K is equal to delta G naught over minus, and then we'll take it. I'll skip a couple of steps here. And so we're going to end up with delta G naught over RT. This is delta G naught at temperature T. So if we have, and this is K at temperature T. So if we have delta G naught at that temperature, then we can use this to calculate K at that temperature here. And so if this were, let's say, at 298, then we can determine that. The other thing we're going to get is this. If we don't know what delta G naught at that temperature is, then we can figure it out. We could do it as two calculations, or we can do it as combined as one calculation. That would be minus delta H naught at 298, okay, minus T delta S naught at 298, ln divided by RT. That would be another option. sometimes we just leave it in terms of ln and k. And so these are some equations all right here. So this equation, if we're given k, we can figure out what delta G naught is. Or if we're given delta G naught, we can figure out what k is. If we're at understand conditions, but not, if we're understanding, actually we don't have to be understanding conditions. This is a little weird because over here, this is non-standard, but this is standard. And so are we at standard conditions or are we not at standard conditions? In this scenario here, we're not at standard conditions because what we're doing is we're taking standard conditions and correcting it by factor. And so this doesn't mean we're at standard conditions. This is just we're under non-standard conditions and we're correcting it. And so this is what we end up with here. And so this is at when we don't have delta G at the temperature T, we'll have to estimate what delta G at that temperature T is. So this is just estimating delta G at that temperature T, which would be this numerator term here. Okay, since we're on the topic of K, which is the equilibrium constant, we have one more equation that's pretty important, and that is we'll leave it like this. This is ln K at temperature T. We're going to call this at temperature T1. ln K at temperature T1 is going to equal, it's going to equal, let's solve this. It's going to equal minus delta G naught over RT. Right, okay. T, and I'm going to call this T1 here. But this has to be delta G naught at T1. Well, we don't necessarily know what delta G naught at T1 is. So what we're going to have to do is we're going to have to replace this with delta H naught at 298 minus T delta S naught at 298. And then this is going to be, this is T1 here, this is going to be RT1 here. Okay, let's try to simplify this a little bit here. And this is going to equal, let's see, a minus, okay, I'm going to do this, delta H naught over RT1, okay, plus, let's do a delta S naught over R. We have 298. All right, then we'll do the same thing here with ln K at T2. Ln K at T2 is going to equal minus delta H naught at 298 Kelvin over RT2 plus delta S naught over R 298. Okay, why am I doing this? Why I'm doing this is just to show you the derivation of this equation, which is a very useful equation. And so what we're going to do is we're going to take ln of K at T2 minus ln of K at T1. And so we'll take T2 minus T1. So this minus this. And so what I'm going to get is, I'm going to get this. I'm going to factor out the minus delta H naught over R. That. So I'll get minus delta H naught over R. 1 over T2 minus 1 over T1. And then I'll do delta S naught over R minus delta S naught over R. Well, that's going to equal 0. And so I end up with this equation. And then I'm going to use the property of logs here. This is going to be ln of K at T2 over K at T1 is equal to minus delta H naught over R. This is at 298 Kelvin. 1 over T2 minus 1 over T1. And so what this allows us to do, this is a very powerful equation because well, actually all this allows us to predict, at what temperature we'll get a certain equilibrium constant. If we know one of them, we can predict the others. So given temperature, we can figure out the change in K, and given the change in K, we can figure out the temperature required to do that. So that's the Okay, there's one other way, which is maybe not as common for getting delta G. And we can use just Hess's law to determine delta G. So this is adding up the equations. When we add up equation 1 with delta G1 plus equation 2 with delta G2, the net equation will just be the sum. And so delta G for the net is just delta G1 plus delta G2. Now the same things apply. If you reverse the equation, we change the sign, etc. It will apply as delta H. So these are all the types of equations. So let's look at some example problems for these. And so one example problem we'll do is this. What pressure will water boil at room temperature? What pressure will H2O boil at 298 Kelvin? So you could boil, what we need is vacuum. And so, it's hard to boil it using the house vacuum, but it's not strong enough. So you use like a simple mechanical pump. It's only 154.
With gravity. Unique job. Katie is
We think of the normal boiling point of water as being 100 degrees Celsius, but that is because we are at 1 atmospheric pressure. This water is currently 21 degrees Celsius. We're going to evacuate the jar and make the water boil.
Looks like we have a vacuum tube here. We're just going to suck the air out of here. You have to watch out for implosions. So usually you have an implosion or explosion shield.
As the pressure surrounding the water decreases, the less the water molecules to escape. You can see that the water is boiling, and we might expect it to be 100 degrees Celsius, but let's check its temperature again. As you can see, it's very close to its initial temperature. The water boiled, but the temperature didn't change.
Okay, so what was that pressure? So let's try to figure out what that pressure must have been. That was well, we'll just do 298. We'll just do 25 degrees C pressure. So the first thing is, okay, what equation are we going to use for this? So one thing is, if we're changing the pressure, that's going to be non-standard conditions, right? And so the non-standard conditions, we know that delta G at temperature T under non-standard conditions is equal to delta G naught under standard conditions at temperature T minus or plus RT ln of Q. Now Q is just the products of the reactants, so Q is equal to the partial pressure of water over 1. This is gaseous water, so Q is just equal to the partial pressure of the water. And so this is what we're going to be solving for. Okay, now what we need though is we need this to go spontaneous. Now, under normal conditions, this is non-spontaneous, this is positive. So what we need to do is we need to get this from positive to 0 so that we can go negative. And so we set that to 0. This is going to equal delta G naught at temperature T plus RT ln of K. Now, this is also equal to K because what we want to do is we want this to be at equilibrium. That is, we want this pressure to be at equilibrium with the liquid so that we have boiling occur. Okay, so then that's just going to give us this delta G naught at temperature T is equal to RT ln the partial pressure of H2O. Yeah, negative. Negative RT ln the pressure of H2O. Now we just solve the pressure of H2O, right?
Something that e to the negative delta G naught.
Yeah, this just seems like, yeah, we're just going to use K is equal to E to the minus delta G naught over RT. This is a very common equation, and we use this equation a lot, but there's a problem with this. What is the problem with this equation? Yeah. We know delta G naught at room temperature and standard conditions. What is it? 8.5 kilojoules per mole, but that's not delta G naught at temperature T. We need delta G naught at temperature T. And so for this one, what we're going to do is, we'll just go ahead, we're going to do it all in one equation then. We need to put in our delta H naught minus T delta S naught here. And we're going to use these at 298 and 298, and then divided by RT. You see why we had to do that? We had to do that because this is, oh, actually, wait a minute. Do we have to do that? This is delta G naught at temperature T. Do I have delta G naught at temperature T?
Yes.
Yeah.
Because the temperature is at 298.
But I'm not at standard conditions. Can I do this?
Yeah, because we're using it as the correct.
Right. Because we're using it as a correction. We're taking our standard and correcting it. And so even though I'm not at under standard conditions, I still can use this under standard conditions because correction to that. And so I don't have to do this. This is just extra work. I could do this, but I'm going to come out with the same number because we had calculated this earlier. This calculated to 8.5, as you call 8.5 kilojoules. So I don't need to do this. And so this is going to come out to E to the minus 8.5, well, 8,500. We'll just go ahead and convert it. 8,500 joules over 8.3145 joules Let's see what that comes out with. So, negative 8,500 negative divided by 8.3145 divided by 298 equals, we'll take e to that. This is what we come out with. I come out with 0.032368. What would the units on this be? You know, K doesn't normally have units, but you know, this is equal to the partial pressure of H2O, which means that even though K doesn't have units, we would convert this to the units of this, which would be 0.032368 bar. Or in other words, about 0.032 bar. So if we could decrease the pressure from 1 bar to 0.032 bar, then we can do it. We can get water to boil at room temperature.
For the K equation, I'm a little confused on when you can't use the GT value.
Well, on a lot of these, let's say we have K at temperature, this is K at temperature T. So let's do some calculations here with K and T. So what we're interested in a lot of is at 298. What is the equilibrium constant at 298 Kelvin? And so let's take a look at delta G's and K, and then just compare it. These are going to be at 298. So this is delta G at 298. This is going to be K at 298 Kelvin. K at 298 Kelvin is just equal to E to the minus delta G over RT. And so what we're going to do is we're going to do this under standard conditions here, like this. And then there's going to be some cutoffs. So the first one we'll do is this. If delta G is equal to 0, what is K equal to? Well, if delta G is equal to 0, then we'll just have e to the 0th, which means it's just K is equal to 1. Here. If delta G, these are our typical cutoffs. If delta G is equal to plus 50 kilojoules, and then we'll go to plus 100 kilojoules, and then we'll go to plus 200 kilojoules. And so let's calculate those. If delta G is plus 50 kilojoules, what is K? So I plug in 50,000. What about R divided by T?
.98.
0.98. Okay. Plus 100. Check in here. I would expect it to be a little bit smaller. Did anybody else get some other number? How about the 100?
Zero point nine six.
0.96. Are you putting in delta G here and dividing by RT and then raising that whole thing to?
Yeah.
Okay.
I'm doing 8.3145.
For 50 kilojoules, so you got 1.7 times 10 to the negative 9.
Yeah, that's
Yeah,
what
that's what I got.
Okay. 1.7. Give me one more digit.
1.72.
2 times 10 to the negative 9. Okay. Yeah, that's more in line. Plus 100. What is it? Yeah, just check to make sure. I do 200,000. I'm doing 200. So I'll do 200,000 negative divided by 8.3145 divided by 298.
96 times 10 to the negative 18.
You have 8.79 times 10 to the negative 36. For 200 kilojoules.
8.79
times
times 10 to the negative 36.
negative 36.
All right. This is the kind of the meaning of this here. When we have a delta G that's up to about 50 kilojoules plus, then we do expect a tiny bit of reactant there, a little bit. But when we get to over plus 50, then it's pretty much all reactant. Because 10 to the minus 36, 10 to the minus 18, these are very, very small numbers. And likewise, if we go negative, so if we go negative 50 kilojoules, negative 100 kilojoules, and negative 200 kilojoules, and then what are the numbers that we get for K?
The opposite side.
Yeah, I guess we could invert it, flip it. But the sign should still stay positive. What is it?
5.8 to the 5.8 times 10 to the 8.
10 to the 8? Okay. How about the 100? Three point 37, 10 to the 17, and the 200?
$1.14 to the 10 times 35.
It's 10 to the 35. So when we go negative this way, we say it's spontaneous. And when we go positive this way, it's non-spontaneous. But what it means is if it's something spontaneous, it doesn't mean the reverse reaction can't occur. The reverse reaction can occur even if it's spontaneous. And so typically what we say is a driving force between plus and minus 50 kilojoules, we'll see, some, in this case, a little bit of product might form, or there'll be a little bit of unreacted reactants that we might have. So this is more of an equilibrium situation between plus and minus 50. And then if we go to, let's say, with driving forces less than minus 50, that is, then this is all product. When I say all product, there's still going to be a tiny bit of reactant. But we still, in Chem 1B, we still do the K, we still do the equilibrium calculation in Chem 1B. In Chem 1A, we wouldn't bother doing that. And so this is kind of relating the driving force here, delta G, to the equilibrium that we expect for this. Okay. Let's see. So let's take a look at some sample problems for this. We actually hit all the equations that we need. So the only thing to do is just to practice a lot of these calculations so that you get familiar with what equations you use in which scenarios. Which I put on my PowerPoint slides some problems. But where did I put my PowerPoint slide?
Might be in files, if you uploaded it, you usually have to upload it if you're there first.
There it is. So let's just quickly look at some example problems here. So if we did the same under standard conditions, we did melting of ice, then we would be looking at this. We would be looking at this process, which goes H2O solid goes to H2O liquid. If we calculate the delta G under standard conditions at 298 Kelvin, then we see that this is going to be less than 0. And if we calculate, then that means there's a driving force for this. So it could occur spontaneously above temperatures of 0. We can figure out what the melting point is just by setting it equal to 0 and then calculating out the temperature. Similar to what we did before. This is where we're talking about the driving force, minimize energy, maximize entropy. This is Boltzmann. This is the number of ways in microstates, the excerpt I have here. This is an equation I did in the video. The number of ways. We really aren't going to do too much with Boltzmann. This is how you calculate or determine absolute entropies. This is a table of absolute entropies here. Appendix D. This is for organics. Even methane, ethane, and propane, these are all gases. And so they're all going to have entropies around 200 to 300. But if you look at methane, its entropy is a bit lower because it has fewer different ways of vibrating, kind of stuff. When you get to more complex molecules like protein, there's more ways it can vibrate and more ways it can rotate. And so its entropy is a bit higher here than some simple molecule like methane, even though they're at the same temperature. These are all 298 Kelvin. So calculating entropies is just the products minus reactants. This is the number one way we're going to determine what the entropy change is. We just look it up in Appendix D and just plug it in here. So this is a magnetite. This is a problem I did in the video. But let's take a look. It gives free energies here. All right, so we're primarily interested in this calculating delta G, whether it's under standard conditions or non-standard conditions. Okay? In this case, it's not specified if it's under standard conditions or non-standard conditions, but we can just look at this and determine it. What we're going to do is we're just going to assume it's under standard conditions and that we're at 298 Kelvin. And so if we're under standard conditions at 298 Kelvin, then these would be all delta H naught, delta S naught, delta G naught at 298. And let's look at the first example here. Here we have dinitrogen monoxide or nitrous oxide decomposing into nitrogen and oxygen. This is a redox reaction here. And so in this particular example, what would delta H be? Be exothermic or endothermic? Well, in this case, it's exothermic. I would have predicted endothermic, actually. I would have predicted this to be endothermic because when we break bonds, it costs energy. When we form bonds, it releases energy. So if this are exothermic, that means that nitrous oxide has unstable bonds compared to nitrogen and oxygen here. So that's a little bit odd, but they're telling us that. Delta S is going to be increasing. And so we end up with this scenario where this is favorable and this is favorable. If both of these are favorable, then it's always spontaneous, but sometimes we have a conflict, like in this case. We go to liquid to solid here. Delta H here, okay, if we freeze water, delta H is going to be negative or positive? Here. It is. Do we have to remove energy or do we add energy to freeze water? Remove, so it's going to be exothermic. So this is going to be favorable. However, the entropy, in order to freeze it, which is more ordered, liquid water or solid ice? Solid ice is more ordered, so the entropy is actually going down. And so this is a case where the enthalpy is favorable, but the entropy is not. And so what we need to do is we need to minimize the entropy term. In order to minimize the entropy term, we need to dial down the temperature. The temperature is going to make the entropy, at least lower temperatures will make it less significant. So this is spontaneous at low temperature. Here, in this case, ammonia, we got to break the bonds to form nitrogen and hydrogen. When we break bonds, this first scenario is very unusual, but normally when we break bonds, it costs energy. It costs energy to break bonds. We release energy when we form bonds. And so here, the delta H is going to be unfavorable, it's going to be positive. And delta S is going to be favorable. So enthalpy is unfavorable, but entropy is favorable. So what we need to do is we need to maximize the entropy term. We maximize the entropy term by doing this at high temperature. So this would be spontaneous at high temperature here. And then this one here, we're going from 3 oxygens to 2 ozones. And so in this case, it looks like we're forming bonds, but ozone is a lot less stable. And so it has very reactive bonds. So this is going to be endothermic, which is unfavorable, and the entropy is going down, which is unfavorable. So this one's non-spontaneous at all temperatures. We can't make this one spontaneous. We could try, but we're going to get a negative Kelvin temperature. So, I mean, the equation work, so what temperature will this become spontaneous? What temperature will this become spontaneous? You might end up with a negative Kelvin. If you end up with a negative Kelvin, then it means no temperature. It will become spontaneous. And so these are our different scenarios here. Standard conditions at 298, standard conditions at temperature T, non-standard conditions at 298. Then we have Q and K. So we just did these calculations here. The cutoffs here around plus 50 and minus 50, where we do equilibrium. But over here, it's pretty much all product. Up here, it's all reactants. So we could do equilibrium as well there. Just shows where the equilibrium calculation is necessary. This is just showing this, extended reaction. This type of diagram is showing, if we were at under standard conditions, in standard conditions is 1 molar, 1 bar. So if you put everything at 1 molar, 1 bar, is it going to want to shift left or is it going to want to shift right? And so if we do this here, for the last problem we did, which is H2O liquid goes to H2O gas, delta G under standard conditions is equal to plus 8.5 kilojoules. What does that mean? What that means is this. If we are under standard conditions, then our initial here is 1 bar. Can we sustain 1 bar of gaseous water at 298 Kelvin? No, we can't. And so what this is saying is that, okay, if delta G naught is 8.5 kilojoules, then what is K for this? Well, K is going to be E to the minus delta G naught over RT. And so if we solve that, we'll get this. For the K, that is 8,500. We'll do 8,500 negative divided by 8.3145 divided by 298, and then take E to that. Oops. So just screw that up and do that one more time. 8,500 negative divided by 8.3145 divided by 298. Take E. .0323. Actually, I didn't have to calculate. I calculated earlier. So that's our K value. So when we look at it, Q, which is 1, is greater than K. Which equals 0.0323. So there's no driving force. In fact, what's going to happen is the reverse reaction is spontaneous. And so delta G of the reverse reaction is spontaneous. And so what's going to happen is there's going to be a change. So we're going to go minus x bar. And so equilibrium, we're going to have 1 minus x bar. And we figure out what x is. So this is what this is kind of showing. What this is kind of showing is if we start off at 1, where do we end up to reach equilibrium? The extended reaction. This one is showing here, that K is much less than 1. This is all reactants. Over here, this is showing K is much greater than 1. This is all products. Or this is at some point we have equilibrium. This you don't have to worry about too much. Non-standard conditions with K and T, and this is the Clausius-Clapeyron equation. So let me talk about some more examples. Actually, I didn't put those examples in there. So an alternate way of figuring this out that we could do is, let's say, here. Let's say I want to figure out what is the temperature when the pressure is equal to 2 atmospheres. Although two atmosphere pressure cooker must be made of very thick metal, and it's got to withstand this pretty high pressure. And so what is the temperature equal to for this? And so there are different ways that we could do this particular calculation. One way is we can use this equation here. Ln of K2 over K1 is equal to minus delta H not at 298 over R, 1 over T2 minus 1 over T1. And since we already calculated a K value, we know that at T1, which is 298 Kelvin, we have K1, which is 0.0323. And so what we want to do is we want to solve for T2 when K2 is equal to 2. So we could do that. And so if I had a 2 atmosphere pressure cooker, I can figure out what the temperature of the water must be boiling at that particular pressure. And then, let's see, fast. Good things, but I'm out of time. So most of the calculations, I'm going to go through examples in the videos. So you can watch the videos. So I'm going to go through calculations. But those are all the equations. It's just putting those to practice. Okay.
Are we in the computer lab?
Oh, tomorrow?